Hi everyone! Yes, I am serious. Today, we will be integrating this monster right here. The integral from 1 to infinity of 2x fractional part of x minus fractional part of x squared all over x squared floor of x squared. And yes, it is an improper integral with the fractional part function and the floor function. And it does have an answer and a really nice answer, so stick around to the end for that. So how can we evaluate this integral? Well, I would like to manipulate our integrand a tiny little bit to get rid of these fractional part functions, and here's how we are going to do it. So our integrand is 2x fractional part of x minus fractional part of x quantity squared all over x squared floor of x squared. And now I would like to factor out a fractional part of x, so this will be fractional part of x times 2x minus fractional part of x all over x squared floor of x quantity squared. And now I would like to make use of the identity that I'll write this in blue, that for all x element of the positive reals, we know that the fractional part of x is equal to x minus the floor of x. It's important that this holds only for the positive reals, because once you get into the negative reals, this identity doesn't work anymore. But then we are integrating from 1 to infinity, which means we are integrating over the positive reals. Therefore, we can use this identity and substitute this in for our integrand to give ourselves x minus floor of x times 2x minus n, which is x, minus floor of x, which is plus floor of x. That floor thing, you look like a parenthesis, there we go, all over x squared times floor of x squared. And now we have gotten rid of our floor function right there, but we can rewrite this a tiny little bit more. So this will be even nicer. On the numerator, we have a difference of 2 squares, which we can expand out to x squared minus floor of x quantity squared all over x squared floor of x squared. And now I would like to divide everything through by x squared floor of x squared. So on the first term, we'll have, since the x squared will cancel out, we'll be left with 1 over floor of x squared. And then on the second term, we'll have the floor of x squared term will cancel out to give us 1 over x squared. Therefore, our integrand is exactly equal to this. And now we can distribute the integral sign to rewrite our integral as the integral from 1 to infinity of 1 over floor of x squared dx minus the integral from 1 to infinity of 1 over x squared with respect to x. And now we'll evaluate each of these two integrals separately, starting with our first integral. And to evaluate this integral, I would first like to recall that a definite integral is basically just the area under a curve. And with that in mind, we can take a look at the Cartesian plane. So this is our y-axis, our x-axis, and now we will sketch the graph of y equals 1 over x squared. So this is the graph of y equals 1 over x squared. And now let's say that this is 1, so this is 1, and this is 2, this is 3, this is 4, and so on. And now we know that the floor of x is simply the greatest integer that is less than or equal to x. And I would like to use this kind of informal definition of the floor function to rewrite it in a more formal definition. So let me do that in green. So we can rewrite the definition of the floor function as, for k being element of the integers, the floor of x is equal to k if and only if k is less than or equal to x is in turn strictly less than k plus 1. And this makes sense because, well, if k is an integer, well, if x is 2.5, say, well, the smallest integer than that is 2, and 2 is indeed less than or equal to 2.5 is indeed less than or equal to 3. And now, this alternate definition is pretty powerful because using that, we can say that 1 over the floor of x squared is equal to 1 over k squared if and only if k is less than or equal to x is less than k plus 1. Which means if, for example, the floor of x is 1, then 1 over the floor of x will be exactly 1 over 1 squared, which is 1. Therefore, using this, we can sketch the graph of 1 over the floor of x squared. So for 1, as I said earlier, if the floor of x is 1, then 1 over k squared will 1 over the floor of x squared will be 1 over 1 squared. So, or f of 1. If we let our function be f of x, then this is f of 1. So the first part of our graph looks a little bit like this. And then if the floor of x is 2, then 1 over the floor of x squared will be 1 over 2 squared. So we can add in that additional part up until the discontinuity at 3. And then same thing for 3. And for 4. And for all the values after that, up until infinity. And now we want to find the area under this red curve. And it's really just adding up a bunch of rectangles. So, like this. But then what are the dimensions of each of these rectangles? So let's say 1 over x squared is our f of x. So this is f of x. And now for this first rectangle, it has a width of 1 and or a length of 1 and a width of f of 1. Second rectangle has a width of 1 and a height of f of 2, as you can see here. Same for this one, it has 1 and then f of 3, and so on, so on, so on. So the area of each rectangle, starting with rectangle 1 all the way to infinity, is 1 times f of k, for k being from 1 to infinity. Therefore, we can rewrite this integral right here as integral from 1 to infinity of 1 over 4 of x on d squared dx as the sum, as k goes from 1 to infinity, of f of k, because it's all the 1 times f of k. But what is f of k? Well, it is just 1 over k squared. And this sum should be familiar to you. It is precisely equal to pi squared over 6. It's also known as the Basel problem because it's named after Euler's hometown, Basel, because we had already too many things named after Euler, so we had to change. So our first integral will evaluate to pi squared over 6. And for our second integral, well, it's way easier than the last. And I'll write this in blue. The integral from 1 to infinity of 1 over x squared. Well, 1 over x squared is just x to the minus 2 dx. And then we can use the power rule for integrals on this one to give us that this is equal to x to the minus 1 over minus 1, which simplifies to minus 1 over x, evaluated at 1 in infinity. And now as x goes to infinity, 1 over x goes to 0, so at infinity this will vanish. And then we'll have 0 minus 1 over 1, which is simply 1. Therefore, our second integral evaluates to 1, which means our entire integral evaluates to pi squared over 6 minus 1. Well, who would have thought that this answer would come up to such an ugly integral? And it is also related to the Basel problem, as I said earlier, which is quite surprising. So, this is the video. Thank you for watching. I'll see you in the next video. Bye.